All right, AP Chemistry, this is your day 42 assignment, lesson 22, calorimetry. So we're dealing with the subject of thermochemistry. So thermochemistry deals with heat that goes into or out of a chemical reaction, just that simple. The reason we're interested in heat is because that represents energy. It's the only type of energy that we deal with in chemistry. And for that reason, if we know how much heat goes into or out of a chemical reaction, we know how much heat is in the chemical bonds that are holding these atoms together. So it tells us all about the energy of the chemical reaction, not just the heat. So we're going to go ahead and study one of the methods that we'll use in class when we get back to school, and that's called calorimetry. And we'll go ahead and describe that process right now. So the question says, using a diagram, list the steps of a constant pressure coffee cup calorimetry process. So we're going to just draw a simple little beaker here, like you would have. Now that really would be maybe a styrofoam cup, and that's what we use. So that's the container, and it's insulated. So it's insulated, meaning that heat cannot come into it or come out of it. Okay, and that's this container right here. Now, what we're going to do is we have water here, and we're going to dissolve. So we're going to dissolve sodium hydroxide into the water. Okay, so this is an exothermic process, meaning that heat comes out of the sodium hydroxide reaction with water. Now that reaction takes place all throughout this solution here. It's mixed in. It's like when you mix salt with water. It's spread out all evenly throughout. It's called a homogeneous solution, meaning that every part of it is like every other part. It's a mixture of NaOH plus water. Okay, but what we're going to do is, just for simplicity, just to kind of visualize this, we're going to just draw it as though the NaOH is just in this block right here in the middle, okay? Separate from the water, but it's really dissolved throughout the water. Okay, so we have three things here. We have a system, surroundings, and the universe. And the first thing we do, let's just describe what we're doing first. This was step number one, actually. So let's define the universe, the system, and the surroundings. So the system is what we're studying, and what we're studying is not the water or the NaOH. It's the breaking of the bonds in the NaOH. That's the system we're interested in studying. So the system is the reaction of the NaOH with the water. It's not either the substance of the NaOH or the water, it's the reaction. It's that process of it reacting. Okay, that's A. We'll give that a sub-letter A. B, the surroundings. Okay, so the surroundings, the heat is coming out of the reaction. It's the breaking of the bonds. The surroundings are what can absorb that heat, what can take it in. And so that is going to be the mass, mostly of the water. Almost entirely the water is going to do that. But you do have the mass of the NaOH, which is really Na ions plus OH ions. They can actually absorb some heat as well. So we're going to say that that's part of what can absorb heat. So that's part of the surroundings. So the mass of the water and the mass of the Na and OH ions are what constitute the surroundings. And finally, C, the universe. The universe is everything inside the container. It's the system plus the surrounding. That's the definition of the universe. Okay, so next step. Okay, so all of the heat that comes out of the system, the reaction, has to go into the surroundings. So the numeric value of those two, that's Q is the heat, are going to be the same. Heat going out of something is a negative. Heat going into something is a positive. So it's the same numeric value. It's just one. It's just for the system, it's going out, it's negative. For the surroundings going in, it's positive. Okay. Okay, the next step, we need to have a thermometer. So here's a thermometer. This symbolizes a thermometer, which measures temperature. We all know that, even before we came into this class. So step E is, it's actually, I should have made this number 3. We're not using letters here. It was letters for system, surroundings, and universe. Now this was step 3. This is step 4. Okay. Okay, so using a thermometer, we measure the temperature increase from that heat going out into the water, and that's the temperature increase of the surrounding. Okay, so using this equation that the heat going into the surroundings equals mass, specific heat, delta T, we calculate the heat entering the surroundings. Now a couple things about this. The mass is the mass of the surroundings. So that is H2O plus NaOH. It's really Na ions plus OH ions, we'll just call it. It's the entire mass that's in there. Everything, because all of that, both the water and the Na and OH ions, are absorbing heat that's coming out of that chemical reaction. Alright, so that's that. This is the specific heat of water. So even though it's a solution of both NaOH and water, there's a small enough amount of NaOH that we don't have to consider what its specific heat is. We just consider the specific heat of water, which equals I'll write it down here, 4.18 joules per gram Kelvin. Okay. Again, specific heat is how many joules of heat does it take to raise 1 gram of water 1 degree Kelvin, or it could be any substance, but in this case specifically that number is for water. Okay, so you use this and you can figure out the Q of the surroundings, the heat entering the surroundings. Okay, we've already determined that the Q leaving the system is equal and opposite to the Q entering the surroundings. So okay, so we already established that the Q, let me get on screen here, the Q, the heat coming out of the system is equal to the heat going in the surroundings, and that's what we just calculated, heat going into surroundings. So if you reverse the sign on Q surroundings, what we calculated right here, we have the heat coming out of the system. Okay, since the heat represents all of the energy in the reaction, there's no other form of energy, there's no light energy, there's no work being done, then that is the total energy of the reaction. Okay, so dividing by the grams of NaOH only, not NaOH in water, because all the energy is coming out of the NaOH. The water is just there to dissolve it. None of the energy comes out of the water. So all the energy we got from this reaction, it comes from NaOH. So dividing by the grams of NaOH only, we can calculate the energy of the energy per gram, or the enthalpy, the delta H enthalpy. Remember, heat and enthalpy, change in enthalpy, are the same thing. So we've been talking about heat all the way throughout the problem, but we can now call that a change in enthalpy. Okay, so by converting grams of NaOH to moles, just a molar mass conversion, it's 40 grams of NaOH per mole, we can compute the energy or change in enthalpy, delta H, per mole of NaOH. This is called the molar enthalpy of reaction, delta H, and we're going to start getting used to this. You abbreviate reaction with RXN, okay, so the delta H of reaction. So that's the entire process. It's important that you have these steps memorized, that you know how to tell this like a story. How does calorimetry take place? And that's going to be something that you will probably have to do on the AP. Not write all of these steps, but you should know the steps, okay? They will ask you questions related to this. Okay, let's move on to problem number 2. Using a diagram, list the steps of constant volume bomb calorimetry. Okay, so let's go ahead and we're going to draw that. It's a little more sophisticated device. First of all, it's a closed container. And inside is a smaller container. And inside of this, you could have some sort of volatile substance, a hydrocarbon. We'll just use the simplest one, CH4, but it could be anything. The problem we talked about in class, the example in the notes, is rocket fuel. It's something that's really going to explode or burn very hot. So bomb calorimetry is used for more extreme temperature situations where you have a greater release of energy. So this is a very solid container. It's not a coffee cup. It's not a styrofoam coffee cup. Outside here you have an igniter. That's just something that ignites. It sets off this fuel. And what you have is a couple wires going down there to do that, to form a spark. That's a little spark right there, and that causes this to ignite. Once that happens, it operates pretty much like a coffee cup calorimeter. You have heat coming out, Q, in all directions. And you also have a thermometer right there, okay? Again, that's a thermometer. Okay, thermometer right there. All right. Okay. Now, so there's some differences in this. It operates pretty much the same as coffee cup calorimetry, except this. So let's go ahead and let's start writing that. Okay, so here the system and the surroundings are different, all right? Before, the system was the water and the sodium hydroxide mixed. The system was the reaction. I'm sorry. So the system is going to be the same here. It's the reaction, the burning of the CH4, the combustion of the CH4. That's what we're really studying here, okay? So let's go ahead, and this is number 1, number 2, and 2A is system. Okay, so that's the system inside of that little box. So that, unlike the last example where we just kind of expressed the NaOH as being in a little box, this really is a box. It's a small chamber that's separated from the water. This is all water out here, and it's pure water. It's not mixed with anything out here. Okay, so this is a little chamber. The heat's going to be able to escape that chamber, but it's not able to escape this. So again, as we did on the last one, let's write insulated. So no heat in or out. That's insulated, this entire large box. Heat can come out of this, okay, as is shown right here in this diagram. Okay, B, what are the surroundings? So here's where it's different. Because the heat coming out is so extreme, we assumed in the last, in the coffee cup calorimetry, in the last experiment, that the heat would be absorbed by the water and the sodium hydroxide. None of it was absorbed by the cup, by the actual container. The heat coming out of this is so extreme that it will not only be absorbed by the water, but it will be absorbed by the container itself. So when we talk about specific heat here, we don't talk about the specific heat of the water. We talk about the specific heat of the calorimeter. Okay, and that is the water and the container. The container could be made out of metal, it could be made out of a number of things, but it's the specific heat of the water and the container put together. And that has to be determined experimentally. There's a special experiment to determine what the specific heat would be of the water and that container together. You do that separately as a separate experiment. But you come into this experiment knowing what that number is, okay? So surroundings. Okay, so this is a long explanation. The surroundings are the water and the container, this, together. And it could be this container too. It's anything that could absorb that heat. So any object or substance that could absorb that heat. So it could be the small container, the large container, or the water inside of it. That's considered the water and the container together. The specific heat used in the calculation is of this combination. That is the water and the container. This specific heat is determined experimentally, okay? So we know the specific heat of water is 4.18 joules per gram Kelvin. We don't know what it is for this container or this container, but we figure that out experimentally before we do this experiment. All right, and C, universe. Okay, so universe is system plus surroundings. It's everything you see there, not the igniter, but everything you see in here is part of the universe, okay? All right. So now we're ready to detonate. So we Okay, so you combust the CH4, you burn it, and all the heat enters the calorimeter. Not just the water, but this entire unit, which causes a temperature increase. And I am again calling that D. I should have called that number 3. The A, B, and C is for system surrounding universe, but I'm actually using numbers for each step. Okay, so number 3. Number 4. Okay, so we're going to modify the formula different than the last one. The last one had mass of the sodium hydroxide and water times the specific heat of the water, which we treated as the specific heat of the sodium hydroxide and water together, times delta T. This one has just C, and that's the specific heat of the water and calorimeter combination. Okay, so again, that's something that's measured experimentally before you do this experiment. All right, so we continue. Sentence. Let's just write this. We've written this before. Negative Q of system. So if we calculated the Q of surroundings, we know that the Q coming out of the system, out of the CH4 up there, out of this, is going to be just the negative of that number, whatever that number is. Okay, so that's the Q of the system. We know that the change in enthalpy, and it is exothermic, so that makes delta H negative. This is going to be a negative. Now we can compute the delta H, the enthalpy per gram of our substance, CH4. So we measured how many grams we had before we went in there. If it was a gas, we could have used PV equals nRT, pressure, volume, temperature, to figure out how many moles. That's a possibility, but assuming we knew how many grams, we're going to just assume we did. Okay, so we just divide that by the number of grams of CH4, not of water, not of anything else. That would be the energy per gram CH4 released. And with CH4, something like CH4, we want to know that, because that's the whole purpose of burning CH4, is to get energy. We're not making something when you do this type of reaction with a hydrocarbon. You're just trying to get energy out of it. All right, and okay, and then if you want to convert the grams of CH4, you know the molar mass of CH4, so you can compute moles of CH4. Then you can compute the molar enthalpy of reaction. That's how much energy per mole of CH4 you can get. Okay, so that takes care of the explanations. This is really the most important part of this assignment, is that you understand this. It may not make sense the first time, but read it and write it several times until it starts to make sense, this process. You need to be able to tell this story of how an enthalpy reaction takes place, both or how a calorimetry reaction takes place, both bomb calorimetry and coffee cup calorimetry. Okay? I'm going to continue the rest of the assignment on another video.